Hello, everyone. Hope you're all excited for the test. It's pretty much finalized and is almost in the process of being printed as we speak. I'm kind of behind on everything and stressed about the midterm just like you guys. Woo-hoo. So this class, I have a few announcements to make about stuff, and feel free to ask me any questions about the midterm/term test that are burning. And then once we're through all that more pragmatic stuff, I'll just keep rambling about design by contract. So first thing that I wanted to mention is that a student in this course requires a volunteer note taker. So I wanted to let you all know of that, so someone can upload their notes to Student Accessibility Services in order to help the student, and also get recognition on your experience record, formerly known as co-curricular record, for your effort. The whole process is super easy. You just take a minute after class to upload your notes to a portal, and it's a good thing to do, so I highly recommend doing that. Next up on the announcements is that I've gotten all assignment 1 submissions, which means that the sample solution is out, so you can check that out. It'll be very helpful once you get the marks back in order to understand what, if anything, you did wrong and prepare for future assignments. You could find it, assuming I uploaded it, in assignments, assignment 1, solution. Cool. The assignment has been given to the markers, and ideally they'll take a week to mark it, which means that the assignment should be returned July 22nd. ~ish. I'll let everyone know if there are any delays in marking, but yeah, you can expect your marks back early next week. And I'm not sure whether to talk about assignment 2 or the test next. I suppose the test is a lot more urgent. So it's going to be tomorrow. It's going to be on paper. During class, you'll have the entire class time. And I plan to make an announcement later today, ideally right after class, detailing which topic specifically will be covered on the test. I wish I could just scroll through it like I will for the assignment, but that would be spoilers. But basically, each question has a specific learning outcome associated with it, and I plan to post the list of learning outcomes that are covered on the test to help you all prepare. The test format is going to be sort of in 3 parts. There are a few multiple choice questions, a few short answer questions, and 1 programming question. The multiple choice is multiple choice. The short answer questions, most of them are honestly, here's some bad code, explain to me why it's bad. And yeah, it's less about, I tried to make the test less about memorization, although you will have to remember stuff, and more about understanding concepts covered in the course. And the programming part, more spoilers, it's going to be pretty similar to the string example we found in class. The question on the test will involve you writing code, and maybe quite a bit of it. But I'm not going to be too picky about syntax or making absolutely sure that it would compile and run. The important part is that you show an understanding of separating interface and implementation, and what bits of code should go where. So yeah, I'm going to repeat all that in a online announcement later, along with specifically which learning outcomes will be covered. But I think that's all I have to say about it for now. Does anyone have any questions about the test? Yes?
Are there any practice tests or exams we can access?
Unfortunately not. I was told not to share it. I think it's because instructors like to take questions directly from past tests, so they're not supposed to distribute past tests to prevent students from preparing exactly. I don't like that. I know that having past or sample tests is really useful for studying, but yeah, I'm not allowed to share them. Sorry. Any other questions?
Will scrolling through slides help to prepare? I mean, or the slides is not enough?
Ooh, Well, hopefully you've been all listening to my ramblings and taking notes. A lot of stuff about dangerous programming techniques is on the test, and that stuff is covered on the slides, but ideally you've been taking notes. But if you haven't, it's not the end of the world, and I would suggest reading through the slides to prepare. Yes?
Is there a question for the memory management?
Yes.
What he asked?
Whether there's a question about memory management, and yeah, there will be. Yes?
And what about dynamics? Is that covered?
Yeah, that will be covered. Both using malloc and understanding why allocating space on the heap is useful compared to the stack, and also why it's also a bit risky. Oh yeah, and I'm fairly sure I mentioned this, but like in a previous lecture, but it is a good reminder. The cutoff for the test is yesterday's lecture. And it's really a short turnaround, and have to apologize for that too. But if we were taking the course at a normal pace, then that cutoff would be the Thursday before the test, and then today would be Tuesday we're reviewing, and the test would be the next Thursday. And then that sure sounds reasonable, but yeah, it's the summer. What are we going to do about it? Regarding that cutoff, yeah, everything I've talked about up to that point is testable, which includes a cursory understanding of design by contract. I know I just barely dipped our toes into it last lecture, but there is one short question about the stuff I talked about yesterday in regards to design by contract. I'll give you all a little bit more in case more questions pop up. Okay, let's talk about assignment 2. And also, if any questions about the term test or the course in general pop into your head while I'm rambling, just feel free to put your hand up. So assignment 2, as if you didn't already have enough to worry about, is going to be out soon. I have the outline completed. I just want to give it another once-over before I actually post it. And I'm going to go over it a bit today. We're going to do more bracket matching. And this time, you're going to implement your own sequential, like not recursive, algorithm, which will use a stack which will use all that stuff about ADTs and interface versus implementation that you've been learning. The bracket matching in question is going to be a bit more intensive than in the first assignment. Previously, the code would just test whether a string contains matched brackets, but this algorithm is going to be able to take the position of a bracket and find its matching bracket, if it exists. The assignment is in 3 parts. First, you're going to make a stack, and you're going to test a stack, and then finally do the bracket matching. You'll probably want to have the string example open to the side while you make this, because it's going to be another very similar application. This time, I'm going to give you the interface, and then it's up to you to implement it. Next up is testing. We're going to talk about unit testing later in the course, quite soon, and how boring it is, but also how useful it is. You're going to make a set of tests, sort of similar to what you were given in assignment 1, but now you're going to make it yourself to test the stack. This will help you make sure that your implementation is correct and allow you to debug a series of implementations that are real bad. You'll get the object files for a series of stacks that are just terrible. And all but one of them's perfect, all but one of them have some sort of problem, but you won't be able to view the code because it's just binary. You'll have to use your test suite from earlier in that question to diagnose the issue. And I guess maybe you can try decompiling those stacks, but that'll probably be more effort than reusing your test suite. I'd be impressed if you did. And then finally, you're going to do bracket matching. The algorithm is described for you here. Basically, it just uses the natural ordering of a stack to keep track of brackets, and you would push open bracket positions onto the stack and then pop when you see a closed bracket. And there's some specific output that you should give. And there's also a bonus where you can do even more intensive bracket matching. You know how in VS Code all your brackets are colored in cool, funky colors? Do that. So instead of taking a position and then finding the brackets that correspond to it, you just color all the brackets that correspond to each other. Also, I should probably elaborate on this output, or input and output. So you get a test case sort of similar to what you saw in question 2 of assignment 1. I promise there won't be any null bytes. A string that may or may not have matched brackets, and an index of the opening bracket that you should find a close bracket for. So this bracket's at index 0, this bracket's at index 1, and then 2, 3, 4, so on. The program finds the opening bracket at that index, and then also is able to point out the closing bracket at that index. And it'll complain if there isn't a match. The README is a bit more intensive than the previous assignment, and that's just because question 2, part 2, pretty much entirely takes place in the README. You'll just have a section for each stack, and you explain like how I messed it up when creating it. And then you use handed, just as usual. So don't pay attention to this tonight. Study hard for the test. But yeah, this course is super fast-paced, and you should definitely get started on it right after the test. For now, though, any questions about the second assignment?
So README file, you just copy-paste yours, right?
For the second question, where you're debugging? Sorry, what were you asking?
For the last assignment, I just copy-pasted yours and just changed the name.
Oh, yeah.
And for this one, it's different.
Oh, so you can definitely copy and paste most of it. Like, all of this stuff is good. But then for you pointing out what makes all those provided stack files so horrible, you, of course, have to write that yourself. You won't get any marks for saying, I'm a bad programmer because, gotta say why. But yeah, I think, oh, and if you're not doing the bonus, don't include the bonus. Basically, you can copy-paste almost all of the README, but be sensible about it. Anything else? Okay, let's design some contracts. Oh, also, design by contract is like a huge part of this. Everything I talk about will have to be implemented in your stack implementation. So where we left off, we were talking about assumptions for a method or for a function. What things need to be true for a function to work correctly, and what things should be true about the output of a function that has worked correctly. I mentioned last time that you can sort of think about it mathematically, but didn't really elaborate on what that means. You could think of it as an implication statement that if the function works as intended, then you should write your function such that if all of these conditions are true at the beginning, then all of those will be true at the end. So let's take a look at some more assumptions, or rather more functions and their associated assumptions. So char at from our string example, with the input, we're assuming that index is a non-negative number, that index is less than the length of the string, and that my string is a valid string struct instance. So its contents are non-null. Its length actually is the length of the string. I would say stuff like that, but the struct string is so simple that I think those really are the only two conditions for it to be valid. And then the output assumptions for this function. So we want it so the character we return is actually in the string, or you can return a different value, in this case, end of string character null, because input assumptions were violated. These things are called assumptions for a reason. It's stuff that you don't usually really think about. You just take for granted when writing your code. And design by contract is sort of meant to highlight or force you to think about those assumptions and make you way better at detecting like edge cases and ways in which execution can go wrong. Oh, and the string we originally had, we also assumed that it hadn't been modified. Might sound like a weirdly obvious thing to point out. Like, of course, char@, doesn't modify the string, but that's an assumption you made. You might accidentally write to the char array when you meant to read it, and that glitch can go undetected, and or maybe any methods or functions that you call during char@ modify the string. Lots can go wrong, and that's why we actually take note of these assumptions we're making. Assumptions don't just apply to functions as well. You could have assumptions that apply to a loop. So for here, we're assuming that each I value is a valid index into the string, for instance. If any of you have taken Comp 2080, or will take it, intro to, or analysis of algorithms, this is very similar to loop invariance that you use to prove correctness of algorithms. So I think this is just going over input assumptions. So whenever you receive a pointer, you're probably assuming that it's not null. When you receive an int, you're often assuming that it's a positive or zero int. You're assuming that indices are within the bounds of an array, that a counter actually reflects the contents of an object. And yeah, like they seem like things that are always true, but bugs always pop up where you least expect them. And so they need to be explicitly stated. So sort of similar to when we talked about functional decomposition, I gave a bunch of theory and then told you how to implement it in C specifically, even though it's not a language-specific thing. Same thing here. We have an idea of how all functions or methods have a set of assumptions about the input and output. Now, what do we do with it? We're not just writing a million comments, are we? So now that we've defined our assumptions, we need to encode them. And that will be done using the assert function. you include assert.h, and then it tests for truthiness. The execution continues if the expression is true and halts if the expression is false. So in this sample code, we have a value 10, and we're asserting that the value is greater than 100. Last I checked, 10 is not greater than 100. So assert will essentially crash the program and give you a helpful error message saying that one of your assumptions has been violated. So you can probably see this being pretty useful. And it also gives us functionality in C that sort of resembles exception handling in other languages. For instance, in Java, you get null reference exception for free. And then in C, you can assert that a pointer you receive is not null before dereferencing it. And then if that's not the case, if the pointer is null, then assert will complain about that. And design by contract goes beyond just re-implementing safety features that are in other languages. Things about whether an object's state is valid, like, trying to think of one for the string example. It's going to be contrived because the string example is contrived, but one assumption we're making is that the length property actually represents the length of the string. It's not just some random unrelated value. More implementation details. We call the input assumptions preconditions. One or more well-defined conditions that must be met before execution. And these check that inputs to function, block, concept. So like, we're mainly dealing with functions, but all these things can apply to loops or even just parts of a function. But if you're thinking about the preconditions for a certain block within a function, you should probably just make that its own function. Whatever. You're checking that the state of the program before you start running that specific bit of code meets certain conditions. So let's implement some preconditions in makeString. I'm going to go back to Aviary. These preconditions, and then we'll later see output assumptions are encoded as postconditions, live in the implementation of a data type. I'm going to zoom out a bit. Hopefully you can still read everything, because I need to be able to read stuff. Okay, so there's at least one assumption that we're making here, and it's that our input char array that we use to build our more complicated string is not null. So Oh wait, first let me add the include statement. I don't usually comment these examples because I'm more focused on showing you all specific coding techniques, but I'm going to comment the preconditions to demonstrate how I personally document them. You don't have to do this. Explain your input and output assumptions however you want. Just make sure it's clear. And this is the technique I happen to use. So I like to use this style of comment to sort of make it look like a title. And then the assumption that we're encoding is that the input, I'm going to call it a char array, same thing as string, but just to differentiate it from capital S string. So for each precondition, I like to put a comment explaining it in plain English, and then the assert statement. And yeah, it's that easy. If we had more input assumptions, we would have more preconditions, which just means more comments and more assert statements. So I'm going to run the program, and you'll find that absolutely nothing changes. I'll compile it first. Cool. Now I'm going to put my bad programmer hat back on, and now finally the program's actually going to call me out for it. I'm going to change the main line to attempt to make a string with null. Oh, the compiler might optimize this out. If this doesn't work, I might have to add a print statement or just some excuse to use my bad string. But anyway, let's see what happens. Oh no! Assertion input is not equal to null failed. That's a pretty nice error message. I'm going to see what happens if we tried pulling this same stunt, but with no precondition, like no assert statement. It might still work, but be set up for failure because eventually you'll try to do something like print the string or modify characters of it, and it'll fail. Or it might get a segmentation fault. Let's see. segmentation fault. So this is a very C-centric example, but as I keep saying, this is useful for all kinds of stuff. Instead of your program just being janky, such as giving useless error messages like these, Design by Contract gives your program the opportunity to make much more specific assessments of what exactly is going wrong in your program. So let's just quickly undo the damage I did. Yeah, that's good. We're keeping it for documentation's sake. Boom. The counterpart to preconditions are postconditions, which are one or more well-defined conditions that must be met after execution. They might be similar to the list of preconditions, but applied to output variables. And they verify that the outputs of a function, block, or concept meet certain conditions. The output of a function most often refers to its return value, but it can also refer to any side effects that the function may have, which just means modifying any memory that's in the heap, such as a setter for a property, like, setter for a property, say the string had the option to change the string it refers to. Wouldn't return a value, but it would modify the struct passed to it. So that's another thing we can verify, that the memory that we modified was modified correctly. So let's do a postcondition or two. So we're going to look at char at. So what might be a postcondition for this? Well, first I think of preconditions, that we should probably check that the index is valid. Oh, and I see a syntax error. And I'm pretty sure I solved before uploading it to the course webpage, but I guess I did that locally. Let's just replace that dot notation with arrow and the direct reference with a pointer. So for our postcondition, we would probably want to check that the char we're returning is actually in the string. For this, we would probably use a for loop that goes through the string and checks each character for being that character. Wear headphones if you're doing that. Okay, sorry. No worries. Where was I? Oh yeah, a for loop will probably work just fine, but there might be a simpler way to do it. I'm just going to rummage through my notes for a moment. Cool. The code in my notes is really weird and makes a copy of the string for the sake of searching through it, and then checks that the original string is equal to that copy. And most of these examples are contrived anyway, but that's sort of next level contrived. I think I'm just going to do the for loop. Yeah, wow. So instead of directly returning or immediately returning the value, I'm going to save it so we can check it. So how do we encode this? Well, I guess I already gave the answer, a for loop. Notice that that's not just a single assert statement. Precondition and postcondition checks should ideally just be one assert statement. They should be as simple as possible and not like change the function's behavior for the sake of checking it. But sometimes you can't do that. Sometimes you need a for loop. And probably a bool variable. Yeesh. Now I don't remember, was our thing for the number of characters in the string length or size? Length. Pretty simple loop. We're just checking each character, and then once we find that the character is in the string, we set found to true. And I guess we can break out of the loop too. Save some precious CPU cycles. And then we're going to pass that bool variable directly into the assert function. I'm not going to bother testing this because, again, this example is super contrived, and I don't even know how we would rig this to make it so self-contents at index is not in the string that it's directly accessing. So we're just going to leave it alone. This is useless. The real lesson here is that you're totally allowed to write extra code to check any assumptions that you're making about the output. Even so, this is still a bit clunky. And if you have a complicated data type that has lots of, or a complicated function that has lots of assumptions about its output, you could very easily see your code getting quite bloated with all these checks. And also at runtime, it'll be running all these kind of useless bits of extra code. So design by contract, or specifically Assert and C's preprocessor, has some solutions to that. Firstly, assertions will only run on debug builds. So Clang and pretty much every compiler on the planet allows you to differentiate between building your code for debugging or release, and probably different configurations as well. Actually, I'm just going to check if this is on the slides to make sure I'm not getting ahead of myself. Cool. I'm just going to ramble about build conditions. So you have release and debug configurations, at least. More complicated projects probably have a bunch of others, but we're just going to focus on release and debug. Debug builds contain some information about things that humans care about, like function names, variable names, line numbers, where important things are located. And these all allow you to use a debugger with your program. When you actually ship a product, those things just sort of get in the way. At best, they're a bit of bloat on on the actual executable file. At worst, they could be a security issue if you don't want people decompiling your code and finding out too much about how it works and finding exploits to it. So release builds don't include this information. Additionally, design by contract is just a debug thing, and it is configured so that when you're debugging, assertions just don't run. It doesn't check those. That's another consideration to speed up your program. So Assert does that automatically. We want to do the same for this silly code we just wrote. And to do that, do a preprocessor if. I think you do if in def dn debug. So you would compile your code with dn debug, do not debug, for release builds, and then if in def checks that the thing it's referring to is not defined. So it's double negative. If do not debug is not defined, then we are debugging, and thus this code should be included in compilation. And we're going to add a corresponding end if. Oh, small correction. It's actually end debug, not do not debug, just no debug. Probably something like that. So this will get caught by the preprocessor, and it will only include this block of code in compilation if you're not debugging, so if you're debugging. And also, for a programmer's sake, if you're using a more elaborate IDE or text editor, or probably even just have the right plugins for Vim that I haven't found yet, you can fold regions of the code so that these things, or whatever is between the if and the end if, just don't appear. That'll let you focus on writing the actual logic behind your program when you want to focus on that, and then focus on preemptively debugging stuff when you want to focus on that. So we have, so far, preconditions that need to be true at the start of a function, postconditions that need to be true at the end of a function, and now we're going to talk about the last little bit of design by contract, which is invariants, things that should be true throughout the execution of not just individual functions, but the entire program. More specifically, they should be true for a specific class or type throughout the life of the program. So you're verifying that the object or data meets certain conditions throughout execution. And it's basically checking a bunch of object properties. One invariant for the string struct that we're probably going to check is that the length property is non-zero. No, non-negative. And we usually implement this as a function that we call at the beginning and end of all these other functions. Yeah, like for the, again, how you choose to organize this is up to you, but what I do is make the invariant check be one of the pre and post conditions. So yeah, let's implement an invariant. So I'm going to make a new function, void check invariant. And it's going to take an instance of our string struct. And now we're just writing conditions that should be true throughout the lifetime of a string. So that length one was a good invariant condition. And another thing that should be true for as long as a string instance exists is that its contents should be non-null. Again, this is all stuff that feels obvious and you would think we wouldn't have to worry about, but if you haven't learned this lesson already, you will learn it by the end of your degree. Bugs catch you off guard. It's all stuff that you thought wouldn't happen, that you thought you're better than, but it happens anyway, and you need to be prepared for that. Sort of like Murphy's Law, what can go wrong will go wrong, and so we want to make a robust system for catching things that do go wrong. And then you could use those same, oh, thank you. So you can use the same preprocessor directives that we used for that sort of clunky post-condition check to make it so this stuff only happens during debugging.
So I have a question.
Yeah.
Is ndebug like a reserved word? Like I specifically need something?
Yeah, like it's, You could definitely think of it like a keyword, like void, int, char, return, stuff like that. So ndebug is defined during the build if you're making a release build, and thus this will register as being defined by the preprocessor. If it doesn't exist, like it hasn't been specified during build, and also I'll show you later how to configure Clang for a release build, then ndebug will be undefined, and the if and def statement will find that it's undefined. So yeah, it is kind of reserved, but not really, in the sense that it's only defined if you tell Clang to define it. Does that help at all? Cool. It'll make more sense as we go. So we have our check invariant function, and I want to note that it's in our implementation. We're not going to put it in our interface. The other coders who use a string, class, struct, thingy, they should just be able to suppose that it works. We don't want them to worry about checking invariants. We're going to do that for them. So because of that, this will only exist in our .c file and not our .h file, which will make it inaccessible to anyone using the string code. So yeah, we just implemented public versus private functions in a language that makes everything public. So finally, we have to actually call the thing. We're going to, or in a real program, you would put a call to it in every precondition and postcondition check, except for the one in the constructor. At this point in execution, at the beginning of the constructor, the string doesn't exist yet. You don't even have anything you could pass to check invariant. And that makes sense. The conditions that should be true for the string's entire lifetime aren't true yet because the string hasn't been created yet. But then, at the end of the constructor, the string is all initialized and stuff, and it should be a postcondition. So yeah, the invariant is separate from pre and post conditions, plays a different role, but you check it as part of pre and post conditions. So, oh, and also, there is one more place where you don't have to check invariant, and that's at the end of the destructor. This makes sense for the equal and opposite reason as not doing it at the beginning of the constructor. The thing that should be true for the entire lifetime of the string doesn't need to be true after the string is, well, dead. So I won't waste our time copying and pasting the invariant check onto every function, but on more robust code, such as the stuff on the assignments, ideally every method or every function would have preconditions and postconditions, including the invariant check when relevant. And also, sometimes a method really does make no assumptions about its input. Say you have a function to print a hard-coded message, and it doesn't take any parameters, doesn't reference any memory from elsewhere in the program. That would have no preconditions. You should probably still use an invariant check if you have one. But in that case, you don't have to make up a super arbitrary one, but you should write a comment explaining why there are no preconditions. We don't have any functions like that in our string example, so I can't demonstrate that. Anyway, like I said, in more robust code, you should have precondition and postcondition checks, including invariant checks, in every function when necessary. But I'm just going to fill in the pre and postcondition checks for char at. Then we'll have an example of one function done well, and you'll know what to do when you have to do this to everything. So one of our preconditions is that the invariant is always true. And then while we're at it, let's incorporate or encode some assumptions we're making about the input to char at. So, First thing I thought of is that the pointer that we're being given, we assume that that's not null, but or that would be a good precondition if we're taking some other object of a type that we're not like actively making functions for. But since this is the string implementation, and we know that of course a string pointer should always be non-null, I'm going to put that in the invariant instead. Yeah?
So sorry, do you put the invariant at the pre and the post condition?
Yeah.
Okay. And it's always its own method, generally speaking?
Yeah, like, I don't really see how else you can do it. Maybe if you only have one assertion for your invariant, you could just write that assertion for the invariant. But in general, yes, the invariant should be its own function. So we've already covered that the string input should be valid, which includes not being null. Now we have the index, which is of a signed type. So it can be negative, but that would be nonsensical for us accessing our array. So we're going to encode that assumption. Wait, non-null, what am I typing? Negative. And we're also assuming that index is a valid index, and luckily with C strings that are properly null terminated, we can actually know the length of it and check. So index is a valid index into the char array. Have to think for a second to make sure I'm using the right comparison operator. So we're going to use strlen to get the length, and strlen will return the size of the array -1, and the maximum valid index is the size of the array -1, but that's where the null pointer is, so we're going to have to use the size of the array -2, which is strlen -1. If you're trying to figure that out for yourself during an assignment, I highly recommend drawing a picture of memory as tape and labeling indices. There's a very high chance that I got that calculation wrong and I should have done a drawing, but whatever. So, what was I just saying? Less than strlen self-contents. Yeah, this looks good. So like if self-contents had 8 characters, then we're making sure that index is from 0 to 7. Yay. We also could have done less than or equal to strlen self-contents -1, but this one's more simple. Anyway, where were we? I think these are good preconditions, and now we should do some postconditions. The order of assertion or order of assertions doesn't really matter. Your assertion, or the order of assertions shouldn't matter. If your invariant checks or more complicated condition checks actually change the state of the program, you're doing it wrong, because you should be able to just remove these and have a perfectly fine release build. That said, I like putting the invariant checks at the start of the pre and post condition list, sort of to just get them out of the way. Consistently putting them at the end of the list would do the same thing. It's just better in both cases than having the invariant check just somewhere random in the middle. Cool. Now I'm just going to make sure, or compile this, probably not run it because our behavior is unchanged, but just using the compiler as a syntax checker, basically. Woo! Oh, did I not declare found? We have 5 minutes left, and if I run out of time fixing syntax errors, I'll just fix them on my own before uploading this to the course website. This course isn't about syntax errors. Okay, so first things first, forgot to declare check invariant. This function exists at the bottom of the program, and in C, for historical reasons, you need to check the invariant you have to declare a function before you use it. So for the rest of our type, this is just fine because our declarations are stored in string.h. But remember that check invariant is basically a private function, local to only the code within string.c. So we've got to put our declaration here. Oh, and there's at least one more error that I know I made. I'll just preempt this. I should include std_bool.h for bool types. And I'm pretty sure I never declared the found variable. Oh no, it's here. Oh wow, that took away a lot of errors. I might do this in time. So conflicting types for char at. Oh, didn't put the updated signature in the interface. Okay, syntax errors checked. That's really it for our little design by contract tutorial. In the next two assignments, you'll be expected to have precondition and postcondition checks for every function that you make, and invariants, which are included in the preconditions and postconditions for every type. So now you're hopefully able to define the pre and post conditions. Oh yeah?
So you only do pre and post conditions for kind of interface stuff, right? You wouldn't do that in main methods or things like that?
Oh yeah. Yeah, because the main function is so self-contained that it doesn't really make sense to do design by contract for it. It has no input, and it outputs an exit code 0. So yeah, excellent question. Don't worry about it. An exception to that, however, is something we haven't covered in the course, but is still useful to know for command line programs, which is arguments. It's possible to make a main function that takes an array of strings, and then those strings will be input for the program. That's actually how all of the Unix commands work. Like, if I'm able to cd into a directory, that cd program has a main function that takes an argument, or a parameter, whatever you want to call it. In that case, main suddenly does have input, and you would want to do precondition checks on that. But for our purposes, don't worry about it. So you should be able to define pre and post conditions, define invariants, and then use those to validate runtime behavior of an ADT, which is a fancy word for a type, such as our string struct. So that's it for now. I'll see you all again at the term test. Good luck.